Welcome back, everybody. So we're going to continue where we left off, which was with logarithmic differentiation, a very, very useful application of implicit differentiation. So just as a small recap, so implicit differentiation is the process of taking the derivative of both sides of an equation and treating y as a function of x, meaning that we're thinking of y as like y of x. So when we take its derivative, it's going to require, in almost every case, it's going to require a chain rule. That's why the derivative of y squared was 2y dy dx. So the reason why that was useful for logarithmic differentiation is that if I apply the logarithms, then the left-hand side is not going to require a chain rule because it's going to be a function of x. So remember, the key thing is that everything in the numerator gets added, everything in the denominator gets subtracted when you expand out a logarithm. So now what I'm going to do is I'm going to differentiate with respect to x. So diff with respect to x. And so the derivative of f of x, a natural log of f of x, would be 1 over f of x times f prime of x. And so instead of having to do several chain rules with the quotient rule and product rules and all that jazz, all I'm doing then is just taking the derivative of natural logs. So that's going to be 2/3 times 2x over x squared plus 1 plus 1/3 times 5 over 5x minus 9 minus 1/3 times 2x over x squared minus 1 minus 5/3 times 7 cosine of 7x over sine of 7x plus 13. It can take a second. There's a lot going on there. So take a second to make sure you understand where everything came from. And if you don't, that's okay. We can talk about it. But I'd like you to get to that point with your logarithm derivatives. The logarithms have pretty nice derivatives. And you can combine, like you can bring in the coefficients if you want to, like the 2/3, the 1/3, the 1/3, and the 5/3 if you want to do that, which I'm going to do once I do the last step. Yes. Yes, absolutely. Imagine if I said no. How terrible of a teacher. So, the derivative of this by the chain rule is going to be 1 over the inside, so 1 over x squared plus 1 times the derivative of x squared plus 1, which would be 2x. Here, the derivative of, like, it's 1 over 5x minus 9 times the derivative of 5x minus 9, which is 5. Same thing here. Derivative of x squared is 2x. That's why it's 2x on the top. And the last one, it's going to require, it's a chain rule within a chain rule. Because it's going to be 1 over the inside. That's where I've got the 1 over the sine of 7x plus 13 times the derivative of sine of 7x plus 13. The derivative of sine, being the outer function, would be cosine. And then I guess I should write it like this, maybe. I should write that 7 over here to make it more fun, like more visual in what we're used to seeing. But times the derivative of the inside, the derivative of 7x would just be 7. That's where that's all coming from. Is that okay? So, any other questions on that? And therefore, the last step, because we don't want to know what 1 over fx times f prime of x is equal to. We want to know what f prime is equal to. So we'll multiply both sides. Multiply both sides by f of x to get that f prime of x will equal f of x, which is the third root of x squared plus 1 squared times 5x minus 9 divided by x squared minus 1 times sine of 7x plus 13 to the 5th. And yes, this is going to be a long thing to write out, absolutely. But it would be far, far worse to write it out without logarithmic differentiation, I assure you. But if you are really truly bored in the next couple of days, if you are really truly bored, then feel free, be my guest to do this by hand. You will get a different answer. Your answer will look different, but at the end of the day, it will be the same thing. Times in parentheses. Let's combine everything. So that's 6x over 3 times x squared plus 1 plus 5 over 3 times 5x minus 9, though you could distribute in the 3's if you wanted to, minus 2x over 3 times x squared minus 1 minus 35 cosine of 7x divided by 3 times sine of 7x plus 13. Yes. Beautiful. And there it is. So you don't have to, like, remember, this isn't going to be used for anything, so we don't have to simplify it at all. Like, we don't even need to combine the, wait, why did it become 6x, guys? It should be 4x. And that's why you shouldn't simplify, in case you make those silly errors.
2 questions.
Yes.
I didn't realize, but I'd say you're probably just introducing the logarithm right now with only x's, right? We didn't do any differentiability with the y's on this problem, right?
Excellent question. Excellent question. So we didn't do any implicit differentiation. We did, but it's a very, very minute piece of it. Because what this was is I wrote f of x, but this is really y. And so I've got the derivative of natural log of y. That is an implicit differentiation. Because I'm doing the derivative of a function of x instead of just of x's. Does that make sense?
Yeah.
So that's why this is that's why we had to wait until we had implicit differentiation to do this, because we could only do that with the knowledge of implicit differentiation, the left-hand side of the equation. That's the first, that's why. So it is implicit differentiation, but a very, very minute form of it. The main thing is utilizing the logarithm to do it. And your second question?
And then if we were to try to find, I'm sure maybe we present like this, but we could in theory find a slope, but if we had a point by plugging something in for the specs.
God help us solve that's the question. That it would be quite annoying to figure out. But yes, if we wanted to find the tangent line, we'd plug in the x value or whatever and go from there.
Yeah, I see actually at this point, the only thing when I was reviewing the videos, maybe it's a good time since you mentioned that f of x is equal to y right there. The only thing that I cannot make a connection to, this might be out of order, but when we're doing higher order derivatives, it really irks me that it's like, what is it, like d2y over dx2, but and then in the video you had like, well, d over dx times the next thing we got d squared. But it seems like, I guess the simplest way I ask that question is the exponent always just the order of the derivative? So like the second derivative is going to be d squared.
Yes.
d3.
So the third order derivative would be d cubed f over dx cubed. Fifth order derivative would be d5f dx to the fifth.
Then I can just take that. I'm not going to worry about y, but that's a nice consistency. Okay.
Yes, it's all like the number that's there is the which derivative it is. All right. Next thing, the other reason why logarithmic differentiation is very, very useful is for situations such as this. Find the derivative of y equals x squared plus 1 to the x. Now, x is not a number, it's a variable. So the power rule cannot work here. The power rule only works if it's a finite number, like 1, 2, 10, pi, square root 2, any of those ones, fine. But since this is x, we cannot do that. The power rule only works for finite numbers. If you remember, if you go back to unit 2.2, you'll see that the definition is that it's x to the n, where n is some number. and x is not a number, it's a variable. So we utilize the derivative, or sorry, we utilize the logarithm, because logarithms allow us to bring exponents out front. So we're going to apply ln and get that ln of y is equal to ln of x squared plus 1 to the x, which then becomes x times ln of x squared plus 1. By the fact that exponents can be brought up front as multiplication. Ideally, this apply ln, you can just you can write that and then don't worry about doing it and then expanding it. You can do it all in once. Ideally, that's where I'd like you to get to, is just utilizing your properties of logarithms to expand it out as it needs to be. So that is something I can work with. X times natural log of x squared plus 1. That's just a product rule with a chain rule inside of it. But it's far more approachable than x squared plus 1 to the x, because I don't have a rule in that format. So then I differentiate with respect to x. WRT, meaning with respect to x. Natural log of y, the derivative of that would be 1 over y times dy dx equals, and so this is my f, this is my g. So f prime would be 1 times g, natural log of x squared plus 1, plus g prime, which would be 2x. Let's tidy it up. 2x over x squared plus 1 times x. At which point I multiply both sides by y, because I don't want 1 over y times dy dx equals something. I want dy dx equals something. So I multiply both sides by y. And I get that dy dx is equal to x squared plus 1 to the x times natural log of x squared plus 1 plus 2x squared over x squared plus 1. And that is my derivative. This function cannot be differentiated unless we know about logarithmic differentiation.
Why is d prime 2x on top?
So it's a chain rule. 1 over so the derivative of natural log is 1 over. So that's why I've got the 1 over x squared plus 1. And then the derivative of x squared plus 1 is 2x. So I just decided to combine it on top. So technically speaking,
2x times 1 over.
yes. So this would be 1 over x squared plus 1 times 2x. And that's why I just put it over 1 and then I multiply both sides, or I multiply across.
And then why does the x, where's the x go? At the very end.
So that's x over 1. So I've combined it. That's why it's 2x squared now.
Got it. Okay. Oh, and then you're changing the logarithm to an exponential form. You're going back to the exponential form?
Yes. You could leave it as x natural log of x squared plus 1. That's not wrong. It's just usually it looks prettier. It's probably going to be less work to write. It's probably going to take less time to write instead of having to write it out in its expanded form.
Okay, sorry, last question. Isn't that the same term twice? X squared plus 1 to the power of x, and then you have it again with the natural log of x squared plus 1? Or what am I doing wrong?
So that will this is coming from the pink, from multiplying by y. This was the derivative of this side. This thing here was the derivative of this. And then we got 1 over y, but when we multiply by y, since y is equal to x squared plus 1 to the x, that's where it is.
Okay, pretty similar.
Yeah, it just so happens to be very, very similar. You'll see it again with this one. It becomes a little bit, it looks a little bit weird at first. So with this next one, apply ln, you get, apply ln. You get ln of f of x, or you can change it to a y if you want, if it doesn't look as nice that way. And it's going to be sine of x squared times natural log of x. Which is what looks weird. Let's make sure we understand why. Because it's going to be natural log of x raised to the sine of x squared. So the sine of x squared goes out front because it's an exponent. And that's why we've got natural log of x, which looks weird. It does. Absolutely. But it's a function just like you or me. So don't need to judge it.
In other words, you're introducing the natural log outside the parentheses to bring the exponent forward.
Exactly right.
Okay.
Exactly right. And we can do that. That is mathematically valid because if you say that, like, there's a rule that we learned in Math 126. I doubt you remembered it. That says that if m is equal to n, then log of m is equal to log of n, provided that it makes sense. And I've made sure that this function makes sense. Like where it's defined, we can do this. So now that we've got that, now we can differentiate with respect to x. And once again, you don't need to write on a quiz or an exam the apply ln or the differentiate with respect to x. You don't need to write that. It's merely for our notes so that we can look back and say, okay, that's what I did. So differentiate with respect to x. That would be 1 over f of x times f prime of x by the chain rule. And then the derivative of the right-hand side, that is a product. So I'd like you guys to go ahead and compute that product right now. I'll slowly fill in details. It's not a plus or minus. It's just a. So it would be 2x cosine of x squared. That's the derivative of f, the purple function, by the chain rule. And then derivative of g is 1 over the inside, so 1 over ln of x times the derivative of ln of x, which would be 1 over x. Or to write it more pretty, 1 over x times natural log of x. And then f prime g plus g prime f gives you that. We multiply both sides by f. And you get that f prime of x is going to equal natural log of x to the sine of x squared times 2x cosine of x squared ln of ln of x plus sine of x squared divided by x ln of x, just to make it look prettier. But I'm not going to require you to write it pretty.
So G prime, the only reason why it's 1 over ln of x times 1 over x is because of the chain rule referencing that the inside function is also a logarithm. Okay, so if that was a constant, it would have been times 1 over x for the second one.
Yeah.
Okay, and then second thing, so we're on the last couple of problems, anytime we're introducing the natural log, that's why one of our last steps, we have to multiply it again by the function. That creates the 1 over the function. only if we reduce the natural loss.
Yes. So that's only when you're dealing with the natural log, when you're doing logarithmic differentiation. At the end of a logarithmic differentiation problem, you're going to have to multiply by y, whatever y, like whatever the original function is. So the key thing that students ask me all the time, and so I'm really glad that you asked it, Blaze. It's a great question. Is when should I use logarithmic differentiation? Excellent question, Blaze. So when should I use it? Mainly when it would be a lot of chain rules and quotient rules and product rules, like to an umpteen, like to an obnoxious degree. That's one where, I mean, you can still do it with regular stuff. You can still do it that way, but it's really tedious. But the only one where you really have to rely on logarithmic differentiation is if you have a function raised to a function, like f of x to the g of x. That's what all these ones previously were. This is your f of x. This is your g of x. This is your f of x being raised to the g of x being the function x. That's in these cases. There is another way to do it that is very silly, but we don't need to worry about that. It has to do with utilizing e's and ln's, like specifically exponential base, or like the exponential function. So now, if you've noticed, whenever we do implicit differentiation problems, 99% of the time, we end up getting stuff over things. Very scientific wording, I know. But you usually get something on top over something on bottom. And so you can still find tangent lines, and you'll have horizontal tangent lines whenever the thing is equal, whenever the derivative is equal to 0, right? Whenever the derivative is 0, that means that the slope of the tangent line is 0. And the only way that can happen is if the stuff in the numerator is equal to 0. And the only way that you can get an undefined slope would be where the denominator is equal to 0. So that's precisely what we can do now. We can find out where we have undefined tangent lines in general. So if stuff is equal to 0, applies a horizontal tangent line. And if things is equal to 0, you get vertical tangent lines. I don't know why I wrote tangent for that one, but not on the other one. So we're going to change that up. Vertical tan lines. So I'm going to say usually we'll have a horizontal tangent line, or usually has a vertical tangent line where the denominator and the numerator equals 0. In the very rare case where they both equal 0 at the same time, then all bets are off. It could be that you have a vertical tangent line. It could be that you have a horizontal. It could be that you don't have either. Usually, though, what happens when that happens is you have a curve that looks something like this. Wait. Like that. So it has both a horizontal tangent line and a vertical tangent line here. So that can happen with an equation, because an equation isn't necessarily a function. Like, I know you're like all sitting there getting like a twitchy eye saying that's not a function, Phil. That's not a function. That fails the vertical line test. Yes, because it isn't. It's an equation. And so in equations, you can have a vertical tangent line and a horizontal one. That can happen. But if there's ever a situation that I throw at you that requires this, I will make sure that that doesn't happen. That's a very niche area that we don't have to worry about. So find all points where the curve represented by the equation 9x squared plus y squared minus 18x plus 6y plus 9 is equal to 0 has vertical and horizontal tangent lines. Does anybody know what that equation is, by the way? Anybody know what that looks like? You guys learned it in 127. Very close. If it had been 9x squared minus y squared, then it would have been a hyperbola. It's an ellipse. So I don't know necessarily which way it's going to be opening up, but it's going to be an ellipse, which means that we should have 2 vertical tangent lines and 2 horizontal tangent lines. And if we don't, then we know we made a mistake. See, it's important to remember stuff from your other classes. So anyways, we're going to find the derivative. So ddx of the left-hand side is equal to ddx of the right-hand side. So ddx of 9x squared plus y squared minus 18x plus 6y plus 9 is equal to ddx of 0. And that gets us 18x plus 2y dy dx by the chain rule minus 18 plus 6 dy dx equals 0.
Why is y squared of the chain rule and not just?
So we talked about that last time, but you can think of y as a function of x. So this is y of x squared derivative. So the outer function is the second power. So that's why it's 2 times y of x to the first power times y prime of x.
It's just a coincidence, so you think of it like that, you'd still get the same thing as long as you.
Okay.
If you say the right way for 2y, you have to remember that it's dy dx with respect to y.
So that's the procedure is just to say like take the derivative like normal and then tack on a dy dx. But the reason why that's happening is because of the chain. Yes. And so when we do, the next thing we do is we isolate the dy dx terms from the non-dy dx terms. We get parentheses 2y plus 6 is equal to 18 minus 18x. So that tells us that dy dx is equal to 18 minus 18x over 2y plus 6. And yes, we could simplify it. We could cancel it out a little bit. There's a common factor of 2, or we could write it as 9 minus 9x over y plus 3, if you really want to. But since these are linear equations in the numerator and denominator, it's not going to be too hard to solve them. If it was like 18x or 18 minus 18x plus 32x squared, maybe I might factor out the 2. But as it stands, it's not going to be too terrible to work with in either format. So now that we've got it as stuff over things. We need to find out where it's horizontal and where it's vertical. So horizontal, the numerator will equal 0. And so I don't want you to, like, once again, you could memorize this as a fact, and that but I'd rather you understand the intuition. Once again, that's dy dx we're talking about. That will be like that gives you the slopes of the tangent lines. If the thing equals 0, which the only way that could happen is if the numerator equals 0, then you have a horizontal tangent line. And if the denominator equals 0, you're undefined. What's an undefined slope? A vertical line. So yes, you can memorize that as a fact, but if you understand it more as the derivative being a slope of a tangent line and understanding what it would mean to have a horizontal tangent line and what it would mean to be an undefined slope, a vertical tangent line, then it's not any memorization that you need to do. Your brain fills in the gaps. Either way, horizontal means numerator equals 0. That means the 9 minus 9x equals 0, which gives me that x is equal to 1. John Doe student boxes this as their answer. John Doe student's wrong, though. Yeah, like frequently John Doe student's wrong. That's just an x value. It wants the points. Now you might be tempted to say, because like I'm going to start the other one for a second. Vert would be where the denominator equals 0. So you have y plus 3 equals 0. So you get y equals negative 3. And it's tempting to write that the answer should therefore be 1 comma negative 3. But remember, we know that this is an ellipse, so it should have 2 horizontal tangent, like 2 points where it has horizontal and 2 points where it has 2 vertical tangent lines. So it couldn't just be 1 comma negative 3. The thing is, this is the y value when you have a vertical tangent line, not where you have a horizontal tangent line. So what we have to do now is have to figure out what y is going to be. What's y? Exactly right. What's y? Well, that's the X value for a point on our curve. And so all we need to do is plug that X value into the original curve to find the corresponding Y value or Y values. Plug X equals 1 into the OG equation. Is everyone okay with OG meaning original? It's actually not original. It's the original gangster equation. Right? We know our history. So, anywho, I'm going to plug in 1 for X. That's meaning that I've got 9 times 1 squared plus Y squared minus 18 times 1 plus 6 times Y. 6Y plus 9 is equal to 0. That gives me Y squared. So 9 minus 18 is negative 9 plus 9 is gone away. So Y squared plus 6Y is equal to 0, which gives me Y is equal to 0 and negative 6. And I mean, like, you can write out the extra step of saying you can factor out the Y if you want to, but if you're feeling comfortable skipping some algebra, please feel free to.
That's 2 points.
So that's 2 points, which makes sense if you think about an ellipse. So the 2 places where it has a horizontal tangent line, so like, let's just put it over here. They're going to have the same X value, but with different Y values. So it makes sense that I should get 2 different points with the exact same X value. So that's the points 1 comma 0 and negative and 1 comma negative 6, because it's always X comma Y. Similarly, so now that we found Y equals negative 3, we're going to plug that in and solve for X instead. So you get 9X squared plus negative 3 squared minus 18X plus 6 times negative 3 plus 9 is equal to 0. And just as a reminder, if you're plugged, like you can do this in your head ideally, but if you're going to use your calculator to calculate this, please remember to put the parentheses around the negative 3. Depending on your calculator, it might view that as outside of the exponent. And so it would do it, it would just write that the answer should be negative 9 when the answer is actually positive 9. So just be careful of that. But you get positive 9 minus 18 plus 9, so that goes away again. And we get 9X squared minus 18X is equal to 0. That's 9X times X minus 2 is equal to 0, which gives me X equals 0 and 2. So we have 0 comma negative 3 and 2 comma negative 3 because it's X comma Y. Yes.
Right, so I thought, like in relation to quarters and cusps, something was not differentiable with a vertical tangent line. Is it like approach infinity, or is that wrong only if it's like super sharp?
So, it could be that it happens at a cusp. The curve could have a cusp, but it's few and far between. And the instance of a cusp would be like where a derivative simply does not exist, and it's not even vertical. But even a vertical tangent line, the derivative doesn't exist there because it's just like a vertical tangent line would mean that your slope is undefined, which means your derivative is undefined. So
these situations where we're finding actually vertical tangent line, no derivative exists there.
yes. So imagine if you plug in 0 comma, definitely try and plug in 0 comma negative 3 into this, and you'll see that it's going to give you, so let's do 0, you're going to get 9 over 0. So it doesn't exist. And that completes 2.5. And we're going to do a rapid round of 2.6. Honestly, by the way, this question right here, This question's awesome. I highly recommend it. It's very, very fun. It's a great time. You'll be a better mathematician for it. But either way, these are examples. Question 7 is perfect examples of why you might want to use logarithmic differentiation. I'd say A probably can get away with that. You can probably get away without using logarithmic differentiation. And even C and E, you could get away without it, but might as well use it to your advantage if you can. F is a prime example of definitely wanting to do with logarithmic differentiation. But either way, keep in mind, by the way, in this section, if your answer doesn't look like mine, try and factor out 2 negative signs from the numerator and the denominator and see if you get the same thing. Or if you might have solved it with different algebra, the way to check your answer, plug in a random value like x equals 0, y equals 0, or 1, 1, or 0, 1, or 1, 0, or anything like that, and see what you get. If you get the same number that I would get, you did it right. If you got different answers, then it's probably either that you made an error in your calculator or you did something wrong earlier on. Either way, yes.
You should use logarithmic if it's like several functions within functions. Is that to say even on the super simple chain rules, you technically still could use logarithmic? It's just why wouldn't you type thing?
Yeah, exactly right. All right. Derivatives of inverse functions. Now we're gonna do a lightning round of this one because this section, the inverse function theorem, is really, really only useful for upper division mathematics. Any example that I can give you is very, very, very contrived. And so I don't like going over it too much. The proof of the inverse function theorem. So have I talked about Rudin in this class? I don't think I have. It's a mathematics textbook. There's a textbook called The Principles of Mathematical Analysis by Walter Rudin. A famous mathematician who wrote that textbook when he was in grad school, and it's used in grad classes all across the nation. And the thing that's great about that textbook, and also terrible at the same time, is Professor Rudin was very, very, very succinct in his writing. Every single proof he had was very, very concise. He never explained anything in his proofs. It was just only the things that were necessary. He didn't go into it. He wasn't willing to hold your hand and help you out. He wanted you to struggle through it and hate your life. Point being, so like most of his proofs are about a paragraph. Basically, every single proof in his in that textbook is about a paragraph long. The proof of the inverse function theorem is 3 pages long. It's a nightmare to prove. But we'll get to that in just a moment. So key point about inverse functions: if a comma b is on the graph, then b comma a is on the graph of the inverse function. Written differently, if f of a is equal to b, then f inverse of b is equal to a. They undo each other. If a gets sent to b from f, then b gets sent to a backwards from f inverse. But the question, like, just to kind of pique your interest, and this is something the mathematicians did, and this is, and once we see the inverse function theorem, I'll explain once again why Leibniz's notation makes things so great. So, find the inverse function and then find the derivatives. So, f of x is equal to x squared. And do you guys remember how to find the inverse function? Yeah. You guys remember? You change the variables, solve for x, right? Like some teachers say you should switch the variables first. I disagree. That's wrong. That's bad math. But you go y is equal to x squared. You solve for x squared. You get x is equal to the square root of y. Plus or minus, which one should it be? The plus or the minus? Our domain for x numbers is from 0 to positive infinity. So we have to choose the plus sign. Do you need to know how to do that? No, but it's fun to talk about. So f inverse of x is the square root of x, or x to the 1/2. So f prime of x is going to be 2x, and f inverse prime of x is going to be 1/2 x to the negative 1/2, or preferably 1 over 2 square root x. So I'm seeing a little bit of symmetry, right? But not too much. One of them is 2x and the one of them is 2 square root x. How does that relate? Mathematicians were kind of baffled for a little bit. Like, inverse functions are pretty nice. So why isn't it really like, shouldn't it be like 1 over 2x or something like that? Or 1/2 x? Who knows? And then some mathematician, don't know who, was like, well, let's just pick a point. So the graph of the function f has the point 2 comma 4. And the graph of the inverse function has the point 4 comma 2. So I want to find the tangent lines at their respective points. So f prime of 2 would be the slope of the tangent line to f at 2 comma 4. That would be 2 times 2, which is 4, versus f inverse prime of 4, because we're talking about the point on the curve. 2 comma 4 is not on the curve of the inverse function. 4 comma 2 is on the graph of the inverse function. So if I plug in its x value of 4, I get 1 over 2 square root of 4, which is 1 over 2 times 2, which is 1/4. Huh. Reciprocals of each other. Interesting. Was that a fluke? Does that always happen? Mathematicians wondered. And they wondered and they wondered. And then the Leibniz notation people, the rest of Europe, was like, I got it. I got it. Makes sense. This is not a coincidence. This is actually a very, very unique result. And that's the inverse function theorem. So suppose f is a one-to-one function, meaning that it is that it has an inverse, such that f of a is equal to b. If f is differentiable at a, then f inverse is differentiable at b. And further, we have that f inverse of b, f inverse prime of b is equal to 1 over f prime of a. So, to explain why Leibniz notation makes things a lot easier. So, an inverse function would be x equals f of y, right? It's in like we write it in terms of x, but that's kind of a bad way to talk about things. An inverse function is technically a function of your range. And so the derivative should be dx dy. But notice, if you think of it like a fraction, 1 over dy dx is equal to dx dy. You can think of it as a fraction, and then it makes all the sense in the world. That it should, the y, the derivative of the inverse, should be 1 over dy, 1 over the derivative, 1 over f prime. It makes all the sense in the world, and so mathematicians in the rest of Europe saw that, and that allowed them to think about it that way, and that allowed them to work on proving it. So if you know something's true, it makes it a lot easier to prove something. Like not knowing how to even begin, that makes things much harder. But they knew that something should work there, and that's how they figured it out. But either way, what is the point of this theorem? Why is this useful? Finding the inverse of a function is very, very difficult. In Math 126, we talk about it, but in general, finding the inverse of a function is very, very challenging. We only give you the functions that we know are not too challenging to work with. But trying to find the inverse of, say, x sine inverse of x squared plus 32 cosine of x, trying to find the inverse of that function ain't easy. Damn near impossible, if I'm being honest. And so, if for whatever reason, I don't know where this would ever occur, but if you needed to find the derivative of the inverse, you couldn't do it by natural means because you can't find the inverse. But by the inverse function theorem, you can find it by finding the derivative of that function and then plugging in the corresponding value, calling it good. That is the use of it. Now, unfortunately, though, it's not very useful in any sense in the real world. This is mainly used to prove a lot of theorems in later math courses, but not something that we need to know. So I'm not going to test you on it. The only important thing from this section, therefore, is this stuff here. the derivatives of the inverse trig function. I don't need you to know the inverse trig, the inverse function theorem. That's for my 300 and 400 and grad students to know about. That you don't need to know that. This is the more important thing. So the derivatives of the inverse trig functions. At this point, we have everything. Like after this point, we have all the derivatives of every function we need to know. Now, what I will tell you is that you do not need to know these ones. Don't memorize. Much like the derivative of a to the x for any base that's not the e and log base b of x, I can count on 0 hands the number of times I've ever had to compute the derivatives of secant inverse or cosecant inverse. You do not need to memorize them. It's not necessary. The other ones are fair game. And you might be thinking that that's lame. Like, Phil, that's super lame. That's some ragu right there. That's some weak sauce. Is that still relevant, right? Weak sauce. We still say that, right? Randy, you still say weak sauce? Good. Okay. But in Math 182, you're going to be talking about integration, which is undoing differentiation. We're going to start it in this class, but you're really going to finish it in 182. And these types of derivatives pop up all the time. The integrals of these functions pop up all the time. So I need you to know them so you can make sure you work with them properly. But secant and cosecant inverse, if your teacher does that, once again, please email me. Even though we're not in the class together, and I will fight to the death. Unless a joust, maybe. I prefer. I'm better with a sword. So we'll just go with that one instead. Unless it's Chris King, he scares me. He's my department chair. That's why he scares me. Just kidding, Chris. You're very, very nice. So trick to remember these ones. The co-functions have the minus sign. Just like before, the derivatives of the co-functions were the ones that had minus signs. The derivative of the co-inverse functions have the minus signs. So really, all you need to do is memorize the derivative of sine and inverse tangent, and you got the other two automatically. Just by knowing that the co-functions have the minus sign. So. Any questions on that? So find the derivatives of the following functions. Now that we know those ones, we can still just do exactly what we've been doing, finding horizontal tangent lines, finding tangent lines in general, finding second order derivatives, all that jazz. So f of t is equal to sine inverse. Oh, by the way, so for my class, I use that notation instead of the arc sine notation. If you want to change it to arc sine or arc tangent or arc cotangent or whatever, be my guest. But in my class, sine inverse like that does not mean sine of x to the -1. That means inverse sine. Please do not make that mistake. I'll try to make sure on quizzes and exams that I'm very, very particular about it. I will say like that is the inverse function, not the -1 power. But either way, so f prime of t, we're dealing with the inverse function. We're dealing with inverse sine. Inverse sine's derivative is 1 over the square root of 1 minus x squared. John Doe student writes this. What piece is problematic? I'm gonna label them 1, 2, 3, or 4. Which piece is wrong?
It was x squared, so then it's number 3.
Number 3 is wrong. Because it's not like the derivative of sine inverse of x is 1 over the square root of 1 minus x squared. But this is sine inverse of t squared. So it shouldn't be that. It should be this. It should be the derivative of, this is a chain rule. The outer function is sine inverse. Derivative of sine inverse is 1 over the square root of 1 minus x squared. But it's evaluated at the inside function, which is t squared. So it should be 1 over the square root of 1 minus t squared squared times 2t. Or 2t over the square root of 1 minus t to the fourth. Since we're not using this derivative for anything, we can leave it in the unsimplified form, but I just wanted to make it look pretty because it wasn't too much work. Any questions on that?
There's not a lot of cases in this class, so we have to rationalize it short of conjugation, right?
Yeah.
For the most part, we could.
Yeah. Rationalization of denominators is a stupid, archaic thing that we do. The only reason why is because we like seeing square root 2 over 2 instead of 1 over square root 2. It's really the only reason why that's still being done. In this day and age, rationalizing denominators is such a tedious task. All right. Sorry, I'm not angry at you. I'm angry at the concept. I'm angry at the concept of rationalization. You are offended?
I said I'm
Not offended. Okay.
Sorry.
All right. H of x is equal to x tangent inverse of 2x minus 1/4 tangent of 1 plus 4x squared. I'd like you to do this derivative, or at least, yeah, let's have you guys work on that one. I'll slowly fill in details. This problem around, I did. Stupid. The next one. Wait, are we? Oh, damn, we're really ahead of schedule. Excellent. That's a rarity. It's a rarity for me. Excellent. And we can simplify it if we want, but that's what you should get at first. And if you feel comfortable doing some algebra, please feel free. You don't have to write the 1 in front of the tangent inverse. You can write 2x instead of 2 over 1 minus plus 4x squared times x. And you can cancel out the 1/4 and the 8. So I guess if we really wanted to, we could write it as or tangent inverse of 2x plus 2x over 1 plus 4x squared minus 2x secant squared of 1 plus 4x squared. So first piece requires a product rule with a chain rule in it. F prime is derivative of x, which is 1. G prime, derivative of inverse tangent is 1 over 1 plus x squared. This is a chain rule because it's not tangent inverse of x, it's tangent inverse of 2x. So it's 1 over 1 plus, instead of x, it's going to be 2x because it's a chain rule, squared, times the derivative of 2x, which would just be 2. And that's why I've got 2 over 1 plus 4x squared. You can leave it in the unfactored or the unsimplified form. It's just it made it easier to write out. Since we weren't using it for anything, since we're not using it for anything, we don't need to simplify. All right. Any questions on that? Excellent question. I combine the 8x with the 1/4, and that's why it's 2x now. And if you want to see the proofs of any of the derivatives of the inverse function theorems, please feel free to ask at some point. In the interest of time and making sure we have plenty of time to practice these things, I'm going to skip it for now. But if you want to come to my office hours or ask me after class, it's actually pretty clever. It's pretty clever how they work. So the next one. Quotient rule. I don't want to do this one. I don't want to do it. I don't want to deal I put it on here because I had to feel like I had to put a problem that involves the secant inverse. I got peer pressured into it. Do we really want to do it? Sure. Okay, fine. Fine, as my son will say, because he's imitating me. Never realize the nuances until you have a little human who repeats them. So it's quotient rule. F prime. Let's see if I have it memorized. Do I have it memorized? F prime would therefore, since this is just secant inverse of x, there's no chain rule required. It's going to be 1 over the absolute value of x times the square root of x squared minus 1. Am I right? Yes.
That's the one you said we don't have to remember.
Yeah, you don't have to have it memorized. So I'm proud of myself because I don't have this one memorized. This is a ridiculous one that nobody needs to know. And G prime, by the chain rule, it'll be e to the x cubed plus 1 times 3x squared. The derivative of e is itself, so that's why it's e to the x cubed plus 1 times the derivative of the inside. Derivative of x cubed plus 1 is 3x squared, and that's where we are. So f prime g minus g prime f all over g squared gives us the dy dx, or y prime, however you want to write it, is f prime g, so e to the x cubed plus 1 over absolute value of x times the square root of x squared minus 1 minus g prime, so 3x squared e to the x cubed plus 1 times f, secant inverse of x, all divided by e to the x cubed plus 1 squared. And this is as good a spot as any to take a nice little break here. So unless there's any questions on this one. I can't believe, I'm almost in awe. We are ahead of schedule. That is nutso. Okay, so let's take a break. Let's come back at 2:10. Let's do 2:10. Let's get some work on that crossword done. People watching the recording, go do some meditation, whatever you want to do. And we're back. So it is recording, yes. Good. All right, so a couple more in this section. This is really good. This is good news that we're ahead of the schedule because we're about to enter into everyone's favorite section of calculus. Best section ever. You're gonna love it. Everyone's favorite thing. We'll get to it in just a second. I don't want to spoil the surprise. So find the equation of the line tangent to the curve P of x is equal to 6x cosine inverse of x minus 1 when x is equal to 1. So tangent line. I need slope and I need a point. So for the slope, we need to find the derivative. So P prime of x by the product rule, f prime g, so 6 cosine inverse of x minus 1 plus g prime, which would be -1 over the square root of 1 minus x minus 1 squared. Technically times 1, because that is a chain rule. It's just not a very exciting chain rule. So you can skip the 1, but does everyone see why that's a chain rule, technically speaking?
It's always almost a single variable. We keep running into that, right?
Yeah, so like technically speaking, the derivative of e to the x is a chain rule, but like the derivative of x is just 1. So like it doesn't really need to be there. But I'm going to skip right into plus the times 1 and then times 6x. So that's our derivative. So we're going to plug it in for p prime of 1 to find our tangent line. That'll be 6 cosine inverse of 0 plus -1 over the square root of 1 minus 0 squared times 6 times 1. Who remembers what cosine inverse of 0 is? Yeah, let's do it. Come on. So remember, trig takes in an angle, spits out a number. Inverse trig takes in a number and spits out an angle. It goes backwards. And so what you're really asking yourself when you see this, when you see cosine inverse of 0, that's going to equal some angle theta. So what you're asking yourself is, what theta will give me an answer of 0? 90 degrees, because it's because cosine inverse is defined between 0 and pi, or 0 and 180 degrees. So it's pi over 2, 90 degrees. I'm good. I'm glad we all knew that right off the bat. Excellent. Feel free to use your calculator, by the way. It should calculate it for you. But it's fun to just bust that out. It's how you impress the ladies. It's a true story. And this will be -6. So that's 3 pi minus 6. That's our mtan. Yeah, it's a weird number. What of it? It's like 9.3 minus 6. That's like 3.3-ish, 3.4-ish maybe. But it's okay. It's just a number. It's your mtan. Next, we need to find the point, because we're only given the x value. So we need to find p of 1, which is 6 times 1 times cosine inverse of 0, which would end up being 6 times pi over 2, as we already calculated, which is 3 pi. So the point 1 comma 3 pi. This is yet another reason why slope-intercept form is the weaker of the two. Because now all I need to do, y minus y sub 1, y minus 3 pi is equal to m, so 3 pi minus 6 times x minus 1. And if you really want to put that in slope-intercept form, you'd be my guest. I prefer not to. I'll do it. All right, so you'll get y equals 3 pi minus 6 times x minus 3 pi plus 6 plus 3 pi. So you get y equals 3 pi minus 6 times x plus 6. If you really must. Yes.
Time we're getting kind of tables, auxiliary function, we should be doing it in radians.
Yes.
So I should never use it.
Yeah, in this class, always in radians, never degrees. We're not sailing here. We're not shipmates. If we were, then yeah, maybe we try and do all that stuff. But no, we're gonna work with radians. Radians are way better. Any questions on that? So it's the same process we've been doing this whole time. Just now we have more functions to work with. That's a good thing, right? We have more functions to memorize. Who doesn't love memorizing function derivatives?
Coincidentally, so then couldn't we have just, can we always, just if they give us an x value, plug that into the function first and get the y value?
I just like to find the slope first.
We got the same thing in the slope. Well, I guess it's not the same because there's a -6.
Yeah, and like it's because because our derivative ended up having a cosine inverse in it as well. So And yes, we can do implicit differentiation as well. So you can differentiate both sides of this equation. So d dx of the left. Man, I should make my my variable r sometimes. I could say ddr. I remember ddr. It's the hit of the century back in the day. Do they really? Excellent. So sine inverse, the derivative of the left-hand side equals the derivative of the right-hand side. Sine inverse. That has a derivative of 1 over the square root of 1 minus x squared. But this is a chain rule with a product rule inside it. So it'll be 1 over the square root of 1 minus the quantity xy squared times, I'm going to do this one in a couple steps because I want it to really see it, because this one's weird when you first see it. So this is times d dx of xy equals tangent inverse's derivative is 1 over 1 plus x squared, but this is not tangent inverse of x. This is tangent inverse of 4x. So this should be 2/3 times 1 over 1 plus the quantity 4x squared times 4. And by the product rule, the left-hand side will therefore be, so 1 over the square root. I'm going to take care of that exponent, so 1 minus x squared y squared. Times f prime g, so 1y plus dy dx times x, f prime g plus g prime f, equals, that'll be 8 over 3 times 1 plus 16x squared.
So on the left, we just use the chain rule to get into derivatives in order to apply the product rule.
Mm-hmm. So when it comes to this section, there are many different ways to solve for dy dx. I think the fastest way would be to multiply both sides by that square root, and that would get rid of it. But it is also completely fine to FOIL it in first and then isolate the dy dx term. Which would you guys prefer? Do the square root technique? I think that's the right idea. I think that's the easier way to go. The path of least resistance. Times the square root of blah. And that cancels it on the left-hand side. And you get y plus x dy dx is equal to 8 times the square root of 1 minus x squared y squared all over 3 times 1 plus 16x squared. And so that's one of the hardest things about like practice problems in this section, by the way, with implicit differentiation, is that all of the answers might look different if you're checking your work. The best way to check your answer then, if you don't get the exact same thing, is plug in a value. If you get the same number, you probably did it right. Like the chances of you plugging in a number that's like a random number and getting two different, getting the same answer as the solution answer, but it being the wrong function is astronomical. But anyways, so at the end of the day, then dy dx will equal 8 square root of 1 minus x squared y squared divided by 3 times 1 plus 16x squared minus y, all divided by x. But in fact, so people watching the recording sadly cannot see this, but I'm going to put it on the board just so you can see that you could solve it a different way. So that was the original way that I decided to solve it. I decided to distribute that square root into it. and then divide by the x over the square root of 1 minus x squared y squared. But both ways are completely valid. Both ways are completely valid. Any questions on that? So if you want to do it this way, it's fine. But this way was, in my opinion, faster. Yes.
Is it correct? So we did the chain rule on the very first step, but not necessarily because we have to, right? In theory, we could also have just applied the product rule to that, or can we not apply the product rule to the side?
The left-hand side?
Yeah.
No, we can't use the product rule. Like, because it is sine inverse of x times y, we have to do a chain rule first.
Oh, because it is a function composed of another. Okay.
Mhm.
Okay, they're not being multiplied. I see.
No.
It's actually just one term.
Yes, it's just one term. All right. So that's inverse functions. And here is all of the derivative rules. Once again, I'm going to kind of highlight the ones that you don't need to know. That one, this one, this one, and this one.
Don't need them.
Don't need them. Everything else is fair game and should be memorized, should be practiced. Please utilize this as a kind of cheat sheet. Feel free to do like test yourself on it. That's the reason why I included it. But flashcards are great. And those are the derivative rules. Everything else, besides the ones that are highlighted in purple, should be known. And once again, I don't like making you memorize things. I really don't. If I can avoid making you memorize things, I avoid it. But because if you're planning on taking calc, like if you're planning on continuing your mathematical career, you're going to be taking derivatives for the remainder of your mathematical career. I guarantee it. I was still taking derivatives in grad school. So these things are going to be happening so frequently that it's important to have them memorized. That happens occasionally in mathematics, which is such an important thing that you just kind of have to have it memorized. Like the definition, the definition of the limit. If you remember, for all epsilon greater than 0, there exists a delta less than 0. Like there's a delta greater than 0, such that the absolute value of f of x minus L is less than epsilon whenever x minus a is less than delta. I have that memorized because it got used so often. Not like that's grad school though. Like no one uses that besides grad students and math majors. So, all right, we're gonna get a head start and we're gonna have plenty of time to work on everyone's favorite section, related rates, aka word problems, everyone's favorite thing. Every math student's favorite concept, which is word problems, right? I hear the collective sigh of relief that we're going over word problems. You excited? Diego, you excited? Yeah, Diego's excited. We should all be excited. So the thing is, this is actually something that could be valid, like to be done in real life. So suppose a snowball is rolling down a hill at you, right? And as we know, snowballs, once they roll down, they gain mass. They gain more and more snow as it rolls down. So that's saying that the radius of that snowball will increase as time goes on, and so will the volume. And then the further thing we know is that the volume and the radius can be related to each other by the formula for the volume of a sphere. V is equal to 4/3 pi r cubed. So we have two related quantities and we have two different rates. We have the rate of change of the radius and the rate of change of the volume, hence the name related rates. The point being is if we know the rate of change of one thing or multiple things, we can find the rates of change of other things. So step 0 is read the problem, you dingus. Read it, please. Please read the problem. I know it's tempting to just try and speed through it when you're on an exam because you want to get through everything as quick as possible. Maybe leave this problem for after you've done all the problems that you know. Like put a dash next to it on the exam because guess what? There will be one. There at least will be one related rates problem. It's a requirement. It's just a thing that you have to do. And so maybe put a dash next to it and come back to it. Read it carefully because there's a lot of information that's packed into these questions. So make sure you take time to ingest all the important bits and pieces. Did I want to write anything? Yeah, no, I didn't. Step 1 is to draw a picture if possible. Pictures are worth 1,000 words, as they say, and that's very, very true when it comes to related rates and any word problems in mathematics in general. But it can really, really help you. It can start jogging your memory of what type of formulas you might need. And then step 2, after you've drawn your picture, if it's necessary, is to write down what you know and what you want. This, like, I learned this from my math teacher and I loved it because I took calculus in high school and then I took calculus at the university. And I liked my teacher, Professor Taggart's method of doing this so much that I stole it. And so you're going to write what you know and what you want. Under the know section, these could be formulas. These could be rates that you know of. These could be specific values that you know. Anything that you can think of. What's the worst thing that happens? You don't use it. You could, like, maybe you're working with a triangle and you write the area formula and the Pythagorean theorem and the law of sines, and you don't end up needing the law of sines or the Pythagorean theorem, but hey, it's a safety net, right? It's like a calculator when you don't actually need a calculator. It's your safety calculator. You should have at least one formula. If you don't have a formula, you're not doing it right. And it should, like, that formula should involve your desired quantity and rate. And you may have to possibly eliminate a variable by substitution, which we'll see in a couple of problems in a little bit here. Step 3. So let's see here. It doesn't have to be perfect. You don't have to be perfect. Extra info is okay. I'm not going to mark you down for writing extra things. In fact, I might even give you a smiley face writing down things, even if they're not necessary. Then differentiate. Once you found your formula that relates your rates, your desired rates, differentiate your formula with respect to the desired variable, typically T for time. And remember all your differentiation rules, especially chain and implicit differentiation. There's a lot of implicit differentiation here, and I'll explain why once we get to it. Then solve for that I should fix that line. Don't plug in values yet. Don't plug in values yet. Please, 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 please. It's a bigger highlighter. If you plug in values early on, finite values, then you're saying that the thing isn't changing. It's fixed. If you plug in a, like, if it's set, like, you'll see in the example, but if you plug in a number early, then it becomes fixed instead of a rate. And so we'll see that in action in a second. Then you're going to solve for the desired rate, where you plug in the known rates and known values of variables, and you're all good. And then step 5 is to reflect on the problem, specifically reflect on why you're taking Math 181 and not doing a much more fun degree. No, I'm kidding. Just reflect and make sure that it makes sense, right? If the volume is increasing by 1 centimeter cubed, and you get that the radius is increasing by 3,000, that might be an issue, right? That might be something to say, like, I must have done something wrong. Or if you know that, like, something is increasing in size, but your rate of change is negative, that might be an issue. So make sure that it makes sense in the context of the problem. Now, here are most of the formulas that you might need to use. I will provide them. You do not need to memorize these formulas. You do not need to have the formulas memorized, especially the surface area formulas. They're ridiculous. But I'll provide them as a fun little cool thing though, just as a fun observation. If I have a function f of x, oh, it's a highlighter, a of x, let's say a of r. A of r is equal to pi r squared. What's the derivative of a of r? Two pi r. The derivative of the area of the circle is equal to its circumference. Similarly, here's the volume of a sphere. Take the derivative of that, you get the surface area of a sphere. Why? Excellent question. I'm glad you asked it. Any other questions? I don't want to answer that one, but it's very, very interesting when that happens. Only happens with spheres. Only happens with circles and stuff. But very, very cool. Just a fun little wow. Such great. Anywho, where am I getting to? So yeah, you don't have to have those memorized. And for my class, I'm basically always going to make you round to 2 decimal places. That's what I'd like. So let's look at that initial example of talking about a snowball that's rolling down the hill. It's coming towards you. As the snowball rolls downhill, I don't know how you did it, but you figured out that the rate of the radius is increasing at a rate of 0.45 inches per second. You have apparently immaculate vision, and you can figure that out right off the bat. But you can't figure out the rate of change of the volume. I know. Suspension of disbelief. So find the determine the rate of change of the volume when the snowball's radius reaches 11 inches, 14 inches. So step 0, we've read the problem. We've read it, we've understood it. Let's do step 1. Yeah, I get the full thing. So step 1. So there's this hill. And here we are at the bottom. And there's a giant snowball up here. And it's rolling towards us, and it's increasing in size. So we're worried. Okay, that picture gave me a little bit of knowledge. That picture reminded me that I'm dealing with a sphere. So I go back, and by the way, so this chart here and any necessary formulas will be provided probably on the back of the scratch paper piece. So, and I look back at here and I say, okay, surface area. Well, I don't need to find surface area. It's not asking for the rate of change of surface area. It's asking for the rate of change of volume. There just so happens to be a formula that involves this volume of a sphere. So step 2, the way I like to write it is I write know and I write want. So one thing I know is the formula. I know V is equal to 4/3 pi r cubed. Do I know anything else? That it's increasing. Specifically, I know a rate of change of the radius. So I know dr dt is equal to 0.45 inches. So it's dr dt because it's a derivative, it's a rate with respect to time, because as time goes on, the radius is increasing. So that's why it's dr dt. Now, what do I want? Usually the want section only has one thing. I want to know the rate of change of the volume. So I want dv dt. In particular, I want dv dt when r is 14. One thing you'll notice about this section, by the way, I want to be very, very clear about it, and so that you're aware, we'll be jumping around a lot. Like it feels very, very disjointed, these problems, because there's a lot of stuff you might remember halfway through and go back to the drawing board. That's okay. You might think you're on the right path, and then say, nope, that's not going to work. Go back to the beginning. Maybe you forgot about a formula that's really, really useful. Maybe you were trying to use Pythagorean theorem, but you're really just needing to use the area formula, or you just need to use a trig formula or something like that. So it's okay to get back to the starting point. Just keep at it. So now we have everything we want. We have a formula that relates volume, the desired rate that we want, dV dt, to the given rate, r, radius, dr dt. So step 3. I'll take that v equals 4/3 pi r cubed. And then what I'm going to do is I'm going to differentiate with respect to t. And when you're writing this on an exam or a quiz, don't worry about, like, you don't have to write this down. It's just for our notes. So it's going to be ddt of the left-hand side equals ddt of the right-hand side. So ddt of v is equal to ddt of 4/3 pi r cubed. So the derivative of v with respect to t is dv dt. The right-hand side will be 4/3 times pi times 3r squared dr dt. Take a second to try and figure out why you think that would be. Okay, like, you might see it off the bat, and if you do, excellent, kudos to you. But if you don't, try and figure out why it would be 3r squared dr dt. So,
That's right, well, because that's just the power rule, right? But is the 4/3 pi a constant?
yes, so the 4/3 pi, that's just a constant that can be ignored. But the reason why the derivative of r cubed is 3r squared dr dt is, remember, these things are changing with respect to time. So r can be thought of as a function of time. R is a function of time. That is to say, r cubed is really r of t to the 3rd power, which implies that r of t quantity cubed derivative is 3 times r of t quantity squared times r prime of t by the chain rule. The derivative of r, since it's a function of time, you need the chain rule. V didn't require the chain rule because it was just v to the 1st power. If it had been v squared, then you write 2v dv dt. If it was natural log of v, you'd write 1 over v times dv dt. If it was cosine of v, you'd write negative sine of v times dv dt. So it all depends on the function that's involved. Is that okay?
Of time, you mean just because time goes on, r increases.
Yes. So, and the thing is, I'm saying that it's increasing at a fixed rate, but that's not really necessarily true. As it gets bigger, maybe the radius changes out over time. Like, maybe since it starts rolling faster, it's only picking up a little more snow as it goes on. So maybe after 10 seconds, it's picking up 0.45, but after 30 seconds, it's picking up like 0.1. because it's rolling faster. So it is a function of time. It might be a fixed function of time, like just 0.545 flat out every second, but it could be changing over time. Any questions on that? Does everyone see why it's 3r squared dr dt? That's the important thing. If you don't understand that, please ask right now, and I'll try and explain it a different way. Cool. So we have, just rewriting it a little bit prettier, dv dt is equal to 4 pi r squared dr dt. Now we've differentiated. We haven't plugged in any values yet because and why haven't we plugged in values? Because you told me to. Right? SpongeBob running, right? You guys remember that episode of SpongeBob? Because you told me to. No? Have you not watched SpongeBob? It's a great episode. I remember if we have time. Anyways, so step 4. Now we plug in the value. And I'll explain why again in just a moment. Sure, I made an arrow. Of course I did. So we want at r equals 14 inches, dVdt, the desired rate that we're finding, is going to equal 4 times pi times 14 squared times dr dt, which is something that we know, which is 0.45. And if I plug that in and I calculate it, I should get 4 times pi times 14 squared times 0.45. You get approximately 1108.35. And John Doe student, silly John Doe, boxes this in. Why is it going to get marked off 1 point? Elephants? Is that 1100 elephants, right? It's the great joke the mathematicians, your math teachers always say. 1100 what? You gotta know, you gotta tell me what the measurement says, which the measurements are. It is inches cubed per second. Now, you could do that by memorizing the fact that volume is a 3-dimensional object. And so it should be inches cubed. Like area is 2-dimensional. That's why area will be area inches squared, and perimeter 1-dimensional. So that's just inches. So you could memorize it that way, or you can just appeal straight to what's going on. This is 14 inches squared, and this is inches per second. So the 4 pi is just a constant, and so you've got inches squared times inches per second. That's why it's inches cubed per second. So you can find out the measurements in basically every problem. There's one at the end that you can't, and that one you don't have to. That would be a cheap shot for me to do it. But you can always follow the actual unit conversions that are happening in there. Now, why did I say that step where it's like, don't plug it in early? Because if I do this, so V equal, unless there's any questions on that, that is our answer for 1108.
Right.
Yep, that's the rate of change of the volume when the radius is 14 inches. Since the dVdt is right there, it's assumed, but it not like you can write dVdt equals Avery, yes. Yeah, just round to the nearest 2 decimal places. Cool. All right. So why did I say that you can't plug it in until the end? If I instead, so I got 4/3 pi r cubed, and then I plug in 14, I get V equals 4/3 pi times 14 cubed. Now the radius is gone. What this is saying, this is finding the volume at a fixed amount of time, at a fixed point in the rolling down the hill. There's no, like, if I take the derivative of the right-hand side, it's just 0, right? Because it's just a constant. And so by plugging it in early, you're saying that now the radius is fixed instead of being a function of time. So we have to wait until we've differentiated to plug in any values, because otherwise we're calculating it at a fixed time where we can't actually measure it. Does that make sense? So we have to wait until the end. That is the key. Yes.
And like you said, plugging in the 0.45 is kind of assuming that it is fixed. But for now, that's it.
Yes. And so we couldn't plug that in until we had differentiated, because the original formula didn't have a drdt. But after we differentiate, like right here, totally fine to plug in. Right, for people watching the recording, right here, totally fine to plug in 0.45. All right, let's see here. We got 4 minutes. I don't know if we can finish a problem in 5 minutes. But yeah, we can at least. No, let's just call it good. Call it good. That'll be it for today. We'll pick up next time with the rest of related rates. The quiz will just cover 2.5. It'll just cover 2.5. I'm not going to test you on any of the derivatives of inverse trig functions right now. That will be on the exam coming up soonish. But just on 2.5. So just on implicit differentiation and stuff like that. So logarithmic differentiation, fair game. Finding tangent lines of implicit functions, that's fair game and stuff. But nothing on 2.6, nothing on 2.7. All right, guys. If you have any questions, feel free to email me. Otherwise, I'll see you guys on Wednesday for that quiz. Oh, and I don't think it's going to happen. I think I mentioned it before, but there might be a few toddlers coming in to visit, if they can actually get them over here. Toddlers. So the Early Childhood Education Lab is having a little tour of campus, and they asked me if I could let them come to my class to see what it's like. And so I said yes. But it's on the other side of campus, and trying to get 2 to 4 year olds to travel on foot is very difficult. So they might be here, they might not. They might just come early to my other class that's right before you guys. But if they are, just letting you know that it'll happen. I made sure that they won't come during the exam or during the quiz. All right, guys, that'll do it.